Hi, everybody. Thank you for coming to our session. I just want to ask, make sure everybody, you're muted. So Jonathan can give his presentation here. My name is Saskia Koick, and I am here to present Jonathan's, or to moderate Jonathan's session. Just as an FYI, today we will have sessions, we being NCAUG, from 1 to 5:15 p.m. At the close of the day, we will give away door prizes. You must be present to win. Then come back for the special interest groups from 6:30 to 7:30. Those will be women in GIS, GIS leadership, GIS early career, enterprise, and natural resource / environmental. Be sure to check out the NCAUG merchandise on the conference page. All proceeds will go to the scholarship funds. All sessions will be recorded and put up on the NCAUG YouTube page after the conference. It does take a little time. Please be patient. So with all that being said, welcome and thank you for attending our session, the Detecting Erosion Vulnerability in HUC 12 Watersheds. Our speaker today is Jonathan Byham. Jonathan is a strategic account manager for GPI Geospatial and lives in Huntsville, Alabama with his wife and 2 children. Jonathan has a background in GIS, remote sensing and surveying, and studied geography at the University of Northern Alabama and at the University of Alabama. When not nerding out on GIS and mapping projects, he likes to enjoy spending time outdoors and seeing live music. With all that being said, I'm going to release it to Jonathan with the last note that if you have any questions, please put them in the chat. If we have time and it's appropriate, I will interject during Jonathan's session, but if not, we will address them at the end. Thank you, and it's all yours, Jonathan.
Thank you, Saskia. I appreciate that. I am Jonathan Byham. Like Saskia said, I work for GPI Geospatial. I want to thank all of you guys for being here. There's a good group of you guys, and I feel honored. There's 2 other presentations going on at the same time, one of which happens to be Dr. Joseph Kursky, who I've met in person before and is a great speaker. So I thank you guys for being a part of this. This presentation is about detecting erosion and vulnerability in HUC 12 watersheds, as you can read here. And so without further ado, I'm just going to hop right in. So here's a little overview of this presentation. We'll talk a little bit about GPI Geospatial, the overview of this project, the eval methodology, the results of this case study, kind of the summary of this all, and some questions. Like Saskia said, if you have questions, put them in the chat box, and we'll field them as we go. So GPI Geospatial, we are a multidiscipline geospatial firm. We're headquartered in Orlando, but we have offices all throughout the Eastern US, as you see here. Our headquarters 2.0, as you will, is in Charlotte, North Carolina. We actually have 2 offices in Charlotte and an office in Wilmington. We've just recently acquired a progressive land surveying firm called LDSI that was in Charlotte. So they are part of the GPI family now. So we are focused on remote sensing, photogrammetry, land surveying, mapping, and GIS applications, kind of anything relating to geospatial sciences and remote sensing. We own and operate a fleet of manned aircraft, as you can see down here, as well as mobile mapping vehicles, unmanned vehicles. We operate many survey crews with licensed professional surveyors that have static scanning abilities and subsurface utility engineering abilities. So kind of all things surveying, mapping, photogrammetry, GIS, that's what we specialize in. We've been a part of and had a presence in North Carolina since 1995. Paul Bader, who is on this call, he's the president of GPI Geo. He owned and operated a company called IMC and was later acquired by GPI and formed GPI Geospatial in 2017. So we've been a part of North Carolina and do a lot of work in the area and partner with folks. So happy to be here. I think this is maybe our 2nd time sponsoring this conference, but 1st time presenting. So very happy to be a part of this conference. So to kind of get into the meat and potatoes of this presentation, we were tasked by Sheboygan County, Wisconsin's Department of Planning and Conservation to detect and identify areas that were potentially vulnerable to erosion. This was mostly focused on agricultural areas, and we used the eval, so the Erosion Vulnerability Assessment for Agricultural Lands. This is a ArcGIS tool set that was created by Wisconsin's DNR using ArcGIS Pro. We'll dig into that in a second. Essentially, this was a county-wide project to define areas within HUC 12 watersheds that were potentially susceptible to erosion. And the main focus of this was to assist watershed managers and others within the county that are doing conservation efforts to essentially prioritize areas. So where should best management practices and assessment be prioritized? For those who might not know about HUCs or hydrologic unit codes, HUC 12 refers to the 12-digit hydrologic unit code that is attributed to watersheds, and they are the smallest watershed in the watershed boundary data sets. That could be a topic for an entire other presentation, or maybe even a conference if you wanted it to. So there's a link here, you guys can dig in some more of that. But essentially HUC 12 is the smallest, most local sub-watershed area. So this was focused on that type of watershed. So eval is a toolbox. It's a GIS-based tool. It uses readily available topographic, soils, and land use information and data to assess vulnerability of agricultural lands to erosion and nutrient export. So it was developed using the Python scripting language within Esri's ArcGIS ArcMap 10 point whatever version it was when they created it. It is also to be able to be used in ArcGIS Pro, which is what we used for doing this project. Essentially, it exists as a toolbox. It requires ArcMap and Spatial or ArcPro and Spatial Analyst extension. And like I said, it uses a lot of readily available data. It's kind of, you select an area, you select some parameters, you run a geo process, you get to input, you get an output. Based on that output, you run it through a couple other processes. And it's nothing that is, they're not reinventing the wheel. They just strategically put together some geo processes, somewhat like Model Builder, and built their own toolbox. And GPI has also done the same thing, but for this project, we use the eval tool. So there's 3 variables for determining the vulnerability index. Deprioritizing areas, you can see them here that flow internally. The stream power index, so areas that indicating areas that could be erosive or potential for gully erosion, and then using the universal soil loss equation. So we'll dig into all of that. You see the inputs up here: LiDAR DEM, soil erodibility, hydrologic soil groups. One thing that I want to highlight big time is culvert data. Culvert data is kind of the ace in the hole for this project. It was provided by the clients. Wisconsin or Sheboygan County had survey grade culvert data for all of their culverts. So that was pretty significant. So we'll dig into that in a second. So kind of like I say here, first things first, you have to create hydrologically conditioned DEM. So this is the study area. Sheboygan County here. We have an office in Sheboygan. It's just a fun word to say too. But this box here kind of highlights the area. This is Plymouth, Wisconsin, along the Mullet River, which again is just fun to talk about. Also, mullets are making a comeback. Went to the beach a couple weeks ago. Young kids everywhere, rocking the mullets. So who knows? Maybe next NCAUG conference, I might have a mullet. Don't hold me to it. So along the Mullet River, kind of zoomed in here, we wanted to show you, conditioning a DEM. So these are digital elevation models that part of the USGS LiDAR project that's going on nationwide, the 3D elevation program. This is actually QL1, so 8 LiDAR points per square meter with a 10 centimeter RMSE vertical. So again, this is all publicly available data. On the left, you have somewhat of a standard digital elevation model, but we have to use culvert data, which is essentially survey data for where water comes in a culvert and where water comes out. So it's depicted as a line, a 3D polyline, and we use those to condition the dim. So you can see on the right here where we've essentially burned through or cut through the dim to allow water to naturally flow through the dim and model right. So for those who don't know, the USGS LiDAR spec, you don't have to provide culverts as part of that. If you did, 3DEP would be super far behind right now, but it is somewhat of a derivative that you can do in the field. You can do it photogrammetrically or in the office using kind of a couple different ways of doing it. But again, we had survey grade culvert data, which was pretty significant for us. And this again allows, it eliminates digital dams caused by road berms or other natural or man-made features, and correctly models flow paths along the landscape. So there's like 6 or 7 steps that we could dig really deep into, really awesome, but yet nerdy GIS steps. For the sake of time, I will skip those, but if we have some time at the end, or if you guys have questions, we can dig back into that. So, like I said, there's three variables here for determining this index, and one of them is internally draining areas and somewhat deprioritizing these as part of the calculation. So many watersheds include areas that don't directly contribute to surface water, meaning they don't greatly impact downstream surface water quality within a watershed. These are identified using the DIM and a curved number-based estimation of runoff for a given frequency and duration of a precipitation event. So essentially, the larger the storm, meaning the less frequent and the longer duration of it that's selected, the fewer the areas that will be considered as disconnected to surface waters. This part's a little complex here. It's based on land cover condition, and hydrologic soil group. It essentially, without direct field observation, so without going out to these areas, without going out to the Mullet River here in Plymouth, Wisconsin, it essentially creates a best case and a worst case scenario, or a high curve and a low curve. So areas here that are in darker red and orange, they kind of represent areas that might be more internally draining. So again, these are areas that we don't want to use as heavily in the calculation because it kind of creates null or convoluted results. So, you know, again, areas here that would be high number would be areas that drain internally, and others that don't on the low curve. So that's kind of the first step in this, or the first variable of this. The second one would be utilizing and creating the stream power index. So the SPI is a measure of the erosive power of flowing water. It is calculated based on slope and contributing area, and approximates locations where gullies might be more likely to form on the landscape. As you can see here on the left, and I'm sure a lot of you guys, if not everyone, has seen a gully, they're more severe. They're a severe form of erosion, essentially, and generally they're deep, they're wide, and they're too deep and too wide to be tilled over. So therefore, the presence of gullies, they can be an indication of extensive soil loss and nutrient loss. So if there's been a lot of rainfall and a lot of erosion, it's essentially going to remove and export the nutrients within that soil, which makes it a lot easier for just general erosion to happen. So we use slope data, we use flow accumulation, and they're determined by the DIM that we created and conditioned with the culverts. And they are used to determine if a perennial stream or overland flow occur. So SPI, the stream power index, is not calculated for any areas known to be perennial streams, because, you know, if this has water in it all the time, it's not necessarily considered a gully. It's, you know, it's a perennial stream. So this image on the right, it indicates, you know, areas in red that would be more conducive to gully erosion, and that makes sense. You know, you can see where the river was. This is that highway, State Route 57, and this is the Mullet River. So yeah, it makes sense. Areas that are kind of feeding into this stream are more susceptible to gully erosion. So, so we've deprioritized internally draining areas. We've calculated the stream power index, so how erosive water would be in these areas. So we've got a couple things going on here. Got some variables going on. And again, it is easier to overlay this onto an aerial photo, but for our sake, I just included on the left and right. So again, like I said, you can see the river, you can see these areas. It makes sense, you know, these are farm areas, but it looks like this might be a marshy area, an area maybe not managed that much by the landowners or by the county. So now we get to a significant part here, the universal soil loss equation. I'm trying to get my bar up here to go away, but it says estimating soil loss potential, universal soil loss equation. This is something that you guys might have been familiar with, learned along the way in a college class or high school class, a hydro class. But the soil loss potential due to erosion can be estimated using the USLE. The data sets needed to be LiDAR data or elevation data from a DIM, or to create a DIM like we have, soil data, land cover, or cropland data. And the factors here are rainfall, erodibility, slope or slope length, land cover, and land management practices. If you multiply all of these together, you get the universal soil loss equation. So essentially, we're just trying to determine the potential for soil loss in these areas. So first things first, we have our C factor. So our land cover or crop rotation. It's a unitless metric that adjusts the amount of soil loss based on land cover type and the management of that land cover. So based on a series of land cover maps, usually over like a 5-year period or 5-year rotation, you can create, or a crop rotation index or map is created. And you can see this is an image based, using ARC, depicting areas with no agriculture, areas that might be for dairy rotation, pasture, potatoes, cash grains. You get the picture here. The big picture, I guess, is essentially this recognizes areas that are in use, meaning they're being managed and rotated on a yearly or a certain rotation period, versus areas that are not being managed or not in use or not used for agricultural purposes. You have a soil erodibility, so a KFactor. This is, again, more publicly available data. This is soil data derived from the USDA, the GS-Sergo database. It identifies soil types, and based on these soil types, there's different attributes that are inferred. So soil composition or the erodibility of that, or any other type, the PED type, so how big the individual PEDs of the soil are. So all those attributes and characteristics of those soil types will play into the factor of the universal soil loss equation. So just realize there's a lot of us in this presentation. No pressure, all right. So we've had our cropland, we've had our soil. So now we'll do our rainfall or precipitation data. This is the RFactor. So the RFactor is the rainfall erosivity, and it is the cumulative force of rainfall on soil. So it's somewhat a coarse spatial scale, depending on the topography of the area. If we were in the Rocky Mountains, or if we were maybe in Western North Carolina, where there's a lot of topography and especially rainfall and precipitation events, where topography would play into that. So if there was a very heavy rainfall, in Boone, then there's probably going to be more of an R factor. In Plymouth, Wisconsin, along the Mullet River, it's a very flat, this is along the Great Lakes. So it's, this is not a cool, fun graphic to show for this specific project area. I did overlay it onto the ortho. You can see here different gradients. It's a very shallow, coarse spatial scale for this topography. But again, it is important. It plays into the factor here. So your R factor being the rainfall erosivity. So the cumulative force of rainfall on soil. And then important here would be the slope. So you can see here on the left, this is slope measured in degrees. It's a pretty straightforward concept here. Anyone that's ever been out in a rainstorm knows that if you're on a hill or something like that, there's going to be more chances of rainfall flowing faster on a slope. Again, this is the river. This is the highway. So
Jonathan.
Thank you very much. You can see here areas in red are going to be areas that have a higher slope. So, this would be the built up road berm for the bridge and along the stream here, maybe some other areas that have been affected by, who knows what natural topography or land management practices there. So this is slope measured in degrees. One part here was I'll back up just a second here, the land management practice, and that was the P factor. Again, it depends a lot on direct field observation. So for this case, it is a factor of 1. We essentially just multiply it by 1 because, again, for a countywide project that, just a lot of variables up in the air there. So the results being this raster, and again, this is an index, so it's an attribute table as well that has a lot of values, but it's graphically displayed as a raster graphic here. So areas with high soil loss and stream power index will have high erosion vulnerability, which makes sense. If there's a lot of soil that's been lost and a lot of nutrients that have been lost in that area, it's going to be more erosive or more vulnerable or susceptible to erosion. Whereas areas that are internally draining, maybe natural retention or detention ponds, or areas that just aren't being eroded into gullies and things like that, they're excluded and really don't have a factor there. So areas in red are equal areas with high erosion vulnerability. Again, it makes sense. Some of these that naturally slope in that probably aren't managed well, but also, areas that come back here, and we'll back up. Let me see if I get an aerial photo. My apologies, I should have put that there. So you can see some of these areas that are agriculture. So just get a frame of reference kind of along this east and west highway here. There are areas that should be prioritized. Maybe there's some grading that needs to be done. Maybe needs to be some smart ag happening here. Maybe best management practices saying, okay, well, there's a lot of fertilizer being put on these fields yearly, and it seems like a lot of it might be eroded into this, this Mullet River here, and that's not good. That could, pose environmental impacts and end up later on down the road piling up somewhere where we don't need it to be. So again, these are areas that indicate where best management practices should be prioritized. This is, again, exported as a raster. So this is something plus all the variables that we created. All the other factors were delivered to Sheboygan County's Department of Planning and Conservation, but also there's, tabular tables. And then again, this can be brought up with parcel information or a grid. So if you had, your county's parcel information and you wanted to say this landowner has all this data, we can identify this. Let's go meet with them. Let's go see what we can do to make sure that the agricultural practices in this area are being managed, with the best intentions. So in summary, 208, so I think I have a little bit of time here. Using this methodology and toolbox, it does provide a cost-effective approach. I won't tell you what the exact cost was, but it was less than $20,000 for a project like this. It's a very affordable thing. Whether it's Sheboygan County is a decently populated county, but there's plenty of counties in North Carolina and in Alabama, where I'm from, and in other states where we're participating from all throughout NCAUG, where that's an affordable price point. However, culvert data is a big factor there. So having culverts, again, is something that we can do, but this is a cost-effective approach to defining these areas that might be susceptible to erosion. This approach is best suited for agricultural areas. Urban areas, there's a lot going on. There's impervious surfaces, there's buildings, plus there's a whole series of stormwater inverts and culverts and all sorts of things that make it very complex. So again, this is really best suited for agricultural areas. We have this ability to perform this task in areas other than Wisconsin. We've developed this tool to do this other than using the Wisconsin DNR eval toolbox. And again, this is kind of an open source, it's not reinventing the wheel or anything like that. So we have the ability to perform this. We'd be happy to look at areas throughout North Carolina as well as other parts of the US. And this should be utilized, we feel like, by watershed managers as well as other stakeholders that manage land, manage hydrologic bodies of water and things that relate to that. So, this is our presentation and our case study for detecting erosion vulnerability in HUC 12 watersheds. I don't know if we have any questions. I think there might be one up there.
There was one question from Todd
Yeah.
Kesselring earlier. It was around the time you were talking about gullies. He was asking if internally draining more likely to have a sink.
Yes. So a natural internally draining areas would have a sink. So yeah, like a natural retention pond or detention pond, or even a man-made retention pond. Because it's talking about water that's eroding and flowing to other places, of course, that area is essentially draining internally and not affecting it. But yes, that is correct, Todd.
Is there anybody else out there with another question here for Jonathan?
If you don't have one now, but come up with one later, my contact information is here. So you can email me. This is my cell phone. You can call or text me. My LinkedIn profile is here. Go to gpinet.com/geospatial. We're very happy to be a part of NCAUG. Want to give a shout out to John Poplars and Tyler Stentz, who work for GPI Geospatial. They worked hard on doing this actual project, and I worked with them to help put this presentation together. But we're looking forward to doing this type of work across more areas. And I guess one last thing to say is, as there's more USGS data becoming available nationwide, this essentially is a derivative of, a LiDAR. You have to have a DIM, and that's a big thing, a digital elevation model. So as more LiDAR is available, this is again a great approach for using readily available data, soil data, crop and land cover, things like that, to create this type of product for government clients, or even private sector clients that are working with government, folks for as a consultant. So as more data, LiDAR data becomes available, we feel like this is a great, opportunity to use that and move forward with this type of approach.
And you got to say mullet repeatedly, so that was pretty cool.
Hashtag mullet, or as Joseph Sloop said yesterday in the intro, he said, # NCAUG 2021.
Yeah.
So I won't show my age. I'm only 31. I at least know what a hashtag is. So sorry, Joseph, if you're on this call, just playful jab there. But
all right, you've got a lot of great jobs and thank yous. But
Thanks,
I don't
everyone.
see any other questions. And anybody that's still in and hasn't answered the exit poll, if you please do so, we would appreciate it.
And again, we got 2 offices in Charlotte, 1 in Wilmington. So if you're in the area, feel free to stop by. We got offices in Georgia, Alabama, Florida, Virginia, Maryland, Wisconsin, Sheboygan, Wisconsin. If you're ever near the Mullet River, let us know.
That's probably my favorite part. I'm sorry, but
I was really close to putting a guy with a mullet in there just to see if everyone's on their toes, right after lunch, if they were sleeping through. Burning in culverts makes them literally like a ditch over the road. It's using bare earth surfaces essentially. So it would be more like burning it through or under. So it essentially stops the road, and then there's the culvert and then comes out. So it allows it would represent how it would naturally flow. So if you were to go and get an invert, set up a survey rod or GPS and get it, comes in, the water comes in on this side of the culvert and comes out. So burning it creates it more like, I wouldn't say a ditch over the road, but more like a ditch through the road. So yeah, Todd, if you want to follow up, I can send you some more screenshots and maybe some cross sections of what that looks like. I'd be happy to send you an email.
all right. It is 2:15 officially. Thank you very much, Jonathan, for presenting with us, and thank you everybody for attending. But it is time for another session, I think. Maybe a break.
Thanks, Saskia. I appreciate it. Thanks, everyone.
Talk to you again, everyone.